Hey everyone, and welcome. Have you ever just stopped and wondered how our complex, three-dimensional world can be built from the simplest rules you can possibly imagine? Well, today, that's exactly what we're going to do. We're going to go on a journey, starting from the absolute beginning. And since our guide for this is based on a classic geometry text, you'll see some of the original Korean terms on the slides, which is pretty cool. I know, it sounds a little bit like science fiction, right? But that's the journey we're taking. We are literally going to start with the smallest possible thing there is and build our way up, step by step, using the fundamental laws of geometry. So if you're going to build a universe, you need some building blocks. And for geometry, it all comes down to three incredibly simple but really powerful ideas. Let's meet our atoms of geometry. First up, we have the point. You've got to think of this as just a location. That's it. It has no size, no width, no depth. It's just a tiny little pinprick in space that says, hey, right here. This is the spark. This is where it all begins. Okay, so what happens if you take that one little point and just stretch it? Bam! You get a line. It's a perfectly straight path that has no beginning and no end. It just keeps going and going and going forever in both directions. And to round out our big three, we have the plane. This is basically our canvas. Imagine a perfectly flat sheet of paper that just never, ever ends. It extends infinitely in every direction. This is the world where our points and lines get to live and interact. All right, so we've got this idea of a line, but it turns out that simple concept has a few different personalities. And if we really want to build things, we need to get specific about the kinds of paths we're using. So, check this out. A true line, or 직선, is the one that goes on forever in both directions. A segment, or sunbun, that's what we usually think of. It has two endpoints, a clear start and stop. It's what we use to build shapes. But then there's the ray, or 반직선, which is unique. Think of a flashlight beam. It has a starting point, but then it shoots off into infinity in just one direction. That's why the notation is so important here. The starting point always has to come first. So far, all our little geometric atoms have been kind of lonely, just existing by themselves. But now we're going to let them meet. And trust me, this is where our universe starts to get really interesting. So when two lines cross on our big, flat canvas, they meet at exactly one spot. We call that an intersection point, or gyeojeom. This is it, the first moment of real interaction between our geometric atoms. And you know what? That little interaction immediately creates something totally new. The space between those intersecting lines, that gives birth to angles. And all of a sudden, our universe isn't just a bunch of paths, it has shape and form. Now look closely at those four angles that get made. You might think they're just random, but geometry loves order. It loves patterns. So, is there a simple, elegant rule hidden inside this simple X shape? Ugh, you bet there is. See the angles that are directly across from each other? They're like little mirror images. These are called vertically opposite angles, or 맞꼭지각. They always come in pairs, facing each other head-on. And here is the beautiful, simple law. Vertically opposite angles are always equal, always. It doesn't matter how you tilt the lines, the angle on the other side will always be its perfect twin. This is one of the first perfect symmetries in our new universe. So beyond just crossing randomly, lines can have two very special, very important relationships. You can almost think of these as the fundamental forces that bring structure and order to our geometric world. First, you've got perpendicular lines, or 직교. They meet at a perfect 90-degree angle. This right here is the essence of structure. It gives us squares, grids, the stable corners of buildings. It's predictability. And then you have parallel lines, or 평행. These lines are like perfect partners, or maybe train tracks is a better way to think about it. They exist on the same plane, they always stay the exact same distance apart, and they will never, ever meet no matter how far they stretch into infinity. And this is where parallelism gets so powerful. When you take a third line and just slice it across two parallel lines, this cascade of predictable patterns just appears. Corresponding angles, or 동위각, are in the same relative position at each crossing. And guess what? They're equal. And alternate interior angles, the յot각, which are on opposite sides of that cutting line, they're equal too. It's just a perfect, repeating system. So neat. So we've built this fascinating 2D world with all these cool rules. But, we don't live on a flat piece of paper. So for our final section, let's see how things get even more interesting when we take our universe into the third dimension. Now, think about that for a second. In 2D, those are the only two options, right? They cross or they don't. But in 3D space, when you add that extra dimension of depth, is there a third possibility? And the answer is a mind-bending yes. This is called a skew position, or kikoinwichi. These are lines that just fly right past each other in 3D space. They aren't parallel, but because they exist on totally different levels, different planes, their paths will never, ever cross. The easiest way to picture this is an overpass on a highway. The road you're driving on is one line. The bridge that crosses way up over your head is another line. They aren't parallel, right? But you're certainly not going to crash. They are in a skew position. So let's just step back and look at what we did. We started with nothing but a single dot. From there, we stretched out lines, flattened them into planes, and watched as they crossed to create these elegant, predictable rules of angles. With those rules, we built a world of order, and then we discovered surprising new relationships that can only exist in 3D. It's pretty incredible to think that the entire structure of the physical world is built on these foundational, elegant ideas. It really makes you wonder what other profound, simple rules are shaping our reality, just waiting for us to notice them.